Hello everyone, how's it going? My name is Dan the Tutor. Today we're going to be looking at two questions from previous year's free response sections for the AP AB exam for calculus. Both of these questions are very similar to each other. I like to call them the table questions or the Riemann sum questions or the trapezoidal rule questions because almost always you'll see it on the AP exam, at least in every past AP exam I've seen recently. This kind of question shows up at least once. And also, at some point in the problem, they will probably ask us to do a Riemann sum or a trapezoidal rule or something like that. So the first one we have today, this is number 1 from the 2012 exam. Let's go ahead and solve it. The temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w. I want to say something about that right now. First of all, when they say strictly increasing, what that means is strictly increasing. It means f prime of x is going to be greater than 0 for all time t. Why? Because when the derivative is greater than 0, that's what increasing means. The second thing I want to say, the function is twice differentiable. That means not only does the first derivative exist, but it also means the second derivative exists, and we're assuming that that's for, again, all time t. And that's going to play a role if they ever ask us a question such as mean value theorem, or they want to know a question on the second derivative, for instance. You're not going to use that to answer the question, but you are going to use that to support your answer, basically. And I'll explain that when it comes up. Okay, continuing. Where W of t is measured in degrees Fahrenheit and t is measured in minutes, at time t equals 0, the temperature of the water is 55 degrees. What they are saying there is W of 0 equals 55. In other words, when I say W of 0, the 0 is my x value and the 55 is my y value. Okay, so going back up here. The water is heated for 30 minutes beginning at time t equals 0. Values of W of t at selected times for the first 20 minutes are given in the table below. Part A. Use the data in the table to estimate W prime of 12. Show the computations that lead to your answer. Using correct units, interpret the meaning of your answer in the context of this problem. So if the original equation is the temperature of water, and we want the derivative, we need to know that derivative is the rate of change. Yes, derivative is also the slope, but for this problem, we want to use the definition. The derivative is the rate of change. Now, if I want to find W prime of 12, what that means is the x value, or I guess the t value, is 12, and we want to find the derivative value, which we're going to find using the average rate of change formula, which is a formula that I'm not even sure if I've ever given you, but I know for a fact you've seen it before if you've ever taken Algebra 1 before, which I know some of you have maybe done. But the average rate of change basically says is f of b minus f of a over b minus a. You may also know it as y2 minus y1 over x2 minus x1, because that's the same thing. It's kind of just the slope formula from Algebra 1. And the reason why we're using this, by the way, is because if you look at the question, we want to estimate the value of W prime of 12. And in other words, if you want to estimate it, what you're basically doing is saying, hey, 12 is between 9 and 15. So if I just imagine these 4 points right here, making a straight line between 9 and 15, that's what they want you to do. Even though they don't tell you that, that's what they want you to do. So what I'm basically saying is you want to find the rate of change between those 2 points. It's 9 and 61.8 and 15 and 67.9. So it will look something like this if I were to write these points in coordinate form. And I know that this is my A, and this is f of A, and this is my B, and that's my f of B. If you don't like that notation, you can say x1, y1, x2, y2, and you'll get the same answer. So plugging it in the average rate of change formula, I would say W prime of 12 is approximately equal to, and the reason why I'm putting the approximate symbol is because this is an estimate. It's going to be f of b, which is 67.9, minus f of a, 61.8, divided by 15 minus 9. Now this is question 1, so it is the calculator section, which means I'm going to get to plug this in my calculator and save myself a headache on the test. It looks like I'll get an answer of 1.0167. Technically, I only have to round to 3 decimal places, so 1.017, and that's for every question on the AP exam, just 3 decimal places. Also, you'll notice I drop the approximation symbol for an equal symbol after the first time I use it. And that's just because in math, I'm allowed to do that. I don't know why, but that's fine notation. So this is good. Okay, that's it for part A. Oh, no, it's not. Using correct units, interpret the meaning of your answer in the context of this problem. What do we think about that? Well, I would say that the answer to this question was, like we said, it's the rate of change. And the rate of change of what? The temperature of water in the tub. And at what time? 12, is it minutes? Yeah, 12 minutes. So the interpretation, and I guess if they want units, I would say degrees Fahrenheit per minute, because this is measured in degrees Fahrenheit for the temperature, and this is per minute. So I would say the rate of change of the temperature of the water at T equals 12 minutes is 1.017 degrees Fahrenheit per minute. Now that's one thing you can say. I do want to give you a second answer because this would also be correct. And honestly, I'm just going to type this one because I don't feel like writing it. The temperature of the water is increasing at a rate of 1.017 degrees Fahrenheit per minute after 12 minutes. And that's going to do it for that one. Okay, on to part B. Use the data in the table to evaluate the integral from 0 to 20 w prime of t. Using correct units, interpret the meaning of the integral from 0 to 20 w prime of t dt in the context of this problem. So this one's actually kind of confusing, I bet, for most people. Luckily, I know how to do it. This is the fundamental theorem of calculus, part 2. You could even make the argument that this is fundamental theorem of calculus, part 1. But basically, let me tell you in terms you'll understand. If I have the integral of f prime of x dx, well, then that's just f of x, right? Because it's the integral of a derivative. Now, because I have bounds, well, I need to put the long vertical bar and a 20 up top and 0 in the bottom, and then actually plug in f of 20 minus f of 0. We're going to literally do this, but for w. In other words, I'm literally going to write integral from 0 to 20 of w prime of t dt equals w of t evaluated from 20 to 0. So that's w of 20 minus w of 0. Remember, these are the y values from my chart. So in other words, that's going to be, for 0, it's 55.0. For 20, it's 71.0. 71.0 minus 55.0. That's going to be an answer of 16.0. The units, by the way, are just degrees Fahrenheit. And the reason why it's degrees Fahrenheit is because the units for w prime of t are the degrees Fahrenheit per minute, because that's a rate. And the units for w of t is just the temperature, so that would just be degrees Fahrenheit. And then they want us to interpret the answer based on the context of this problem. This is simply saying the change in temperature. I think you understand that once we got the math, like 71 minus 55, that's just the change in temperature from 0 to 20. You just subtract the initial and the final. And the reason how I knew that was true, by the way, I knew it was just the change in the water temperature, is basically because if you take the integral of a derivative and you have some bounds, let's say a to b, then what you get is not just the original function, but because of the bounds, it's the change in the original function. So how I'd write that in English, the water temperature increased by 16 degrees Fahrenheit during the first 20 minutes. And there we go. That's part B. Now part C, for 0 less than or equal to t less than or equal to 20, the average temperature of the water in the tub is that equation, which is true. Use a left Riemann sum. What did I tell you? They love asking Riemann sums for these questions. With the 4 subintervals indicated by the data in the table to approximate that value, does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. So here, let me look at the table. I'm also going to erase what I have down because it's just cluttered. So normally if I want a left Riemann sum, I would follow that formula that we talked about before. If you don't know what I'm talking about, then you can watch my video on Riemann sums on my website. But whenever you have a table, it's slightly different. Also, I want you to notice that they want 4 subintervals, and really what it is, it's the distance between these 4. So in other words, here's 1, here's 2, here's 3, and here's 4. That's how we're going to find our Riemann sum for this one. And you have to use one of the two values for each circle I made. And since it's the left Riemann sum, I'm going to use the left value. So the black is going to use 55, the red is going to use 57.1, the blue is going to use the 61.8, the green is going to use the 67.9, and the 71.0 gets ignored. If we were doing a right Riemann sum, then we would include the 71.0. So this is going to be kind of like the long way of doing a Riemann sum, but it's not too difficult. All you need to do is say the integral from 0 to 20 of w of t dt, because that's why we have Riemann sums, by the way. It's literally to replace the integral. And I would say it's approximately equal to the base times the height for each rectangle. Let me go back up to my table real quick. So the base of each rectangle is going to be 0 to 4, so that distance is 4. The red is going to be the distance from 4 to 9, so 5. I'm just doing 9 minus 4. Then the blue is 15 minus 9, which is 6. And the green is 20 minus 15, so 5. And then the heights of each rectangle are the bottom row. So the first rectangle will be, for the black, it's the 4 times 55.0, plus for the red, it's 5 times 57.1. So I'll write that in here. The blue is going to be a base of 6 and a height of 61.8. And then I ran out of room. Going on to the next line. The last rectangle is 5 times 67.9. Okay, so I'll plug this in my calculator again, and I'll get an answer of 1215.8. That is not my final answer, because remember, we just did the integral from 0 to 20 w of t dt. We still need to multiply by the 1 over 20, like it says to do in the problem. So just divide our answer by 20. We will get 60.79. The units are degrees Fahrenheit. So that's our answer for the average temperature. It's going to be 60.79 degrees Fahrenheit. And they want to know if this is an overestimate or an underestimate. So when it comes to Riemann sums, let me just draw two pictures for you. If I have a graph that, let's say, looks like this, that is strictly increasing, which, if you remember, this was the word they used in the first sentence of this problem, the function's strictly increasing, and I were to actually draw my left Riemann sum on this function, then it would look like this. And you'll notice the last point gets ignored for the left Riemann sum, like we said it would earlier. And this is my area in the shaded red region. So again, that's a left Riemann sum. And if I wanted a right Riemann sum for the same function, well, it would look like this. Something like this. And again, I shade in the area of my blue, and that's my right Riemann sum. And you'll notice when the function is increasing, the left Riemann sum is an underestimate, and the right Riemann sum is going to be an overestimate. So since we want the left Riemann sum, it is going to be an underestimate. And if you want to answer a justification that they'll accept on the AP exam, you just need to say, since w of t is strictly increasing, the left Riemann sum will be an underestimate. And that's all you need to say for your justification. And there's still one more part, part D. For 20 less than or equal to t less than or equal to 25, the function w that models the water temperature has first derivative given by that function right there. Based on the model, what is the temperature of the water at time t equals 25? Yep, so I know what to do for this immediately. So let me try to explain this first in English, and then I'll explain it with the math. If you want to know the temperature at 25, you would first start with the temperature at time 0. You would then add the change in temperature from 0 to 20, and then you would also add the change in temperature from 20 to 25. That's all you need to do to find the temperature at 25. And how would I write this in English? Or, I'm sorry, how would I write this in math speak? I would say w of 0 plus the integral from 0 to 20 of w prime of t dt. Why w prime? Because remember earlier we said that this was the change in temperature. We said that back in part B. and then plus the integral from 20 to 25 of w prime of t dt. So there we go. We're going to add three things together. Now w of 0, they say in the problem, it's 55 degrees at time 0. So that's 55 plus. The change in temperature was actually our answer to part B. So that's 16 degrees Fahrenheit. So plus 16. And then plus the integral from 20 to 25 of my derivative function, which they were so nice to give me in this problem. It's 0.4 square root of t cosine of 0.06t. Make sure your calculator's in radians for this next part. So 0.4 root t cosine of 0.06t. And dt at the end there. So now I'm going to plug in just the integral right now in my calculator. The way I'm going to do that is I'm going to hit Math 9 on my TI-84 Silver Edition calculator. That will bring up the little integral symbol, and I just plug it in. And if I do that correctly, then this integral is just going to be 9.479. I only have to go to 3 decimal places. And then if I add these three numbers all up together, then I'll get a final answer of 80.479. And this is measured in degrees Fahrenheit. Okay, so it looks like that's it for that one. A couple things I want to say. First of all, I just realized that with this table here, since these are the exact temperatures and you start at 55 and then the 71, I could have replaced this 55 plus 16. I could have actually just replaced that with 71. I'll get the answer a little bit faster just by using the last value in the table. But the way I did it is right too, so I don't care. And then the last thing I want to do is, of course, grade this problem to make sure we were doing it right. So here's the scoring guidelines for 2012 exam. So for question 1, we got 1.017. You get 1 point for the estimate and 1 point for the interpretation with units. The water temperature is increasing at a rate of approximately 1.017 degrees Fahrenheit per minute at time t equals 12 minutes. That's exactly what we said. So 2 points for us right there. Since they say estimate, by the way, it means that you do need this little, whatever it's called, symbol, approximation symbol. You are going to need that, or else you're not guaranteed the points. For part B, 1 point for the value, 1 point for the interpretation. They got 16 degrees Fahrenheit, which is what we got. And they said that the water has warmed by 16 degrees Fahrenheit. We said that the water temperature increased by 16 degrees Fahrenheit, which is the exact same thing. For part C, it's 3 points. 1 point for the left Riemann sum, which they didn't even write the answer for the left Riemann sum. But they have all the work here, and I'm pretty sure that this is exactly what we did. It's the area of the 4 rectangles. You get 1 point for the approximation, which is the 60.79 answer, and 1 point for saying an underestimate with the reason. This approximation is an underestimate because the left Riemann sum is used and the function w is strictly increasing. Exactly what we said. And then part D, that's the wrong answer. So I would have lost a point for that one because I had my calculator in degrees and not radians. And my answer was wrong, but this one is right. So the funny thing is I thought I checked. I probably did check. I was just being brainless for a second. But that's going to do it for that one. 8 for 9 points ain't too bad for an AP free response question. You're probably going to get 3 out of 9 on the actual test. And that's not good. I'm just saying the reality. And then the second question I have for us today, this is question 3 from the 2013 free response. As you can tell, it's got the table. We're probably going to do something very similar as the last one. So let's go ahead and try it. Number 3, hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t from 0 less than or equal to t less than or equal to 6 is given by a differentiable function. Remember what differentiable means? It just means that the derivative exists. So in other words, c prime of t exists, where t is measured in minutes. Selected values of c of t measured in ounces are given in the table above. Okay. Part A. Use the data in the table to approximate c prime of 3.5. Show the computations that lead to your answer and indicate the units of measure. This is almost identical to part A we did in the last question, except that part A in the last question we did, that one wanted us to interpret our answer. For this one, we just need units of measure, so we get to save ourselves a step here. But it's the exact same formula. If you want to approximate c prime of 3.5 and you're given this table, you're going to use that Algebra 1 slope definition, the f of b minus f of a over b minus a, specifically between 3 and 4 here. We're looking at these 2 points right here. 11.2, and 12.8. By the way, this is the no calculator section, so no calculator this time. So f of b is 12.8 minus f of a is 11.2, because those are our y values from this table. And then just divided by 4 minus 3. And if I want to write this, I would say c prime of 3.5 is approximately equal to this. This is my setup for the work. You'll notice I never actually plug in 3.5 anywhere. And the reason why is because 3.5 is just somewhere in the middle of 3 and 4. And since they want an estimate, it doesn't matter where I put it. It could have been 3.1, 3.9, 3.7. They asked for 3.5. It's some point between 3 and 4. If I wanted to know 5.5, for instance, I'd look between these points, just so you know. And that's going to be the strategy for this one. We're not done yet. We still have to do the math. 12.8 minus 11.2. That's just 1.6. Divided by 4 minus 3 is 1. Looks like the answer is 1.6. And the units are going to be ounces per... Is this minutes? Yeah, minutes. Okay. If you prefer to write ounces like this, OZ, that's fine too. I don't care. That's good. So that's it for part A. Easy peasy. Part B, is there a time t between 2 and 4 at which c prime of t equals 2? Justify your answer. So whenever I want to know, is there a time, or justify that there's at least one time, or anything where it says something like this, it's either going to be the intermediate value theorem or the mean value theorem. How do I know which one it is? If it's a derivative, then it's mean value theorem. So then in that case, all I need to do is remember the mean value theorem, which of course, the first step of the mean value theorem is just proving that I can use it. Remember, in order to use the mean value theorem, you need to be continuous on the interval from a to b, which in this case is 2 to 4. And that's the closed interval because we need to include the points 2 and 4, which isn't a big deal. And it also needs to be differentiable on the open interval from 2 to 4. So how would we prove that if I don't have a function? I only have a few values here. The way you're going to prove it is you're going to use the fact I said earlier, this is a differentiable function. So we already got that checkbox going. But is it continuous? The answer is yes. Why? Because if it's differentiable, then that means it's automatically continuous. Automatically. You don't even need to check it. So we passed both of our checks. Now we just need to actually use the mean value theorem, which says f prime of some value c equals f of b minus f of a over b minus a. Since they said that they want to prove that c prime of t is 2, that's the derivative, that 2 goes right there. So 2 equals b and a. I believe we're looking between 2 and 4. So we're really looking at this point here and that point there. So 2 comma 8.8 and 4 comma 12.8. So that's going to be 12.8 minus 8.8 divided by 4 minus 2. 12.8 minus 8.8 is just going to be 4. Divided by 4 minus 2 is 2. Looks like we get 2 there. 2 equals 2. We just proved it using the mean value theorem. So when it says justify your answer, you would say this. By the mean value theorem, and I know you can abbreviate that, MVT, there must be at least one time t where c prime of t equals 2. And that's all you're going to write. All the justification came from the mean value theorem. Okay, so that's it for part B. So far this question I think is easier than the last one. That's going to change with part C. Part C is pretty difficult. But once you know how to do it, it's not that bad. Use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of 1 to 6 from 0 to 6 c of t dt. Using correct units, explain the meaning of 1/6 integral from 0 to 6 c of t dt in the context of the problem. So first let's talk about midpoint. I should also say I want my 3 intervals. If you want to easily find the intervals and they're equally spaced, then the width of each of your rectangles is going to be b minus a over n, where b is the top number 6, a is the bottom number 0, and n is the number of subintervals, 3. That's just going to be 2. So in other words, this is going to be one of our Riemann sums. From 2 to 4 is going to be another. And then the last one is going to be from 4 to 6. Now the funny thing is, you see there's some overlap there between 2 and 4. That's fine, not a problem. But what I do want to tell you is that you don't even care about those points. Since you want the midpoint Riemann sum, you need the point in between 0 and 2, which is that one. You need the point in between 2 and 4, which is that one. And you need the point between 4 and 6, which is that one at 5. And the reason why we're doing this, by the way, like we said in the last problem, I forget what part, I think it was part C, the reason why we have Riemann sums is because they approximate the integral. So then basically what I'm saying is that this integral right here is approximately equal to, and I say approximate because this is a Riemann sum, it is an approximate. It's important you have that in your answer. It's going to be the base, which since they all have the same base of 2, I can factor out the 2, times the height of my first one, which is 5.3 from right here. So 5.3 plus the second width here at 3, so 11.2 is my height. And then plus the last one is at 5, that was 13.8. So plus 13.8. Again, I'm not allowed a calculator, darn. But luckily I can do basic addition. 0.3 plus 11.2 is 16.5 plus 13.8. Really don't want to mess this up, especially on the AP exam. 8 plus 5 is 3, 1, that's going to be 0, so 3. Yeah, 30.3 times 2, so that's going to be 60.6. Now that's not the final answer, again, because that's just the integral. They wanted 1/6 times that integral, so 1/6 times 60.6. I'm going to do long division because, again, I don't want to mess this up. So 60.6 divided by 6. That goes into the 6 once, minus 6. That would be 0.6. That's 0. And then 1. Okay, looks like 10.1. 10.1 is my answer. The units are going to be... What were we talking about? Ounces here? Yeah, it's going to be ounces. The reason why it's ounces, by the way, is because I know that this was the average value theorem. And if you don't know why, then you should watch my video on the average value theorem, and then you'll say, oh yeah, this looks exactly like the average value theorem, and obviously you should know that. So when it says to interpret our result for part C and explain the meaning, we're going to say the average amount of coffee in the cup is 10.1 ounces. And there we go. There's our answer for part C. And then finally, part D. The amount of coffee in the cup in ounces is modeled by that equation. I'm kind of confused because I thought that was given by C of t. But I guess we're going to use B of t now. It doesn't matter. Using this model, find the rate at which the amount of coffee in the cup is changing when t equals 5. So if you want to find the rate at which coffee in the cup is changing, that's just the derivative. They're really just asking us, hey, what's the derivative b prime of t at t equals 5? I think it was 5. Let me double check. Yeah, at t equals 5. So this is a new equation, which means I'm not going to use anything from the table or parts A through C for this question. B of t, they said, was 16 minus 16e to the negative 0.4t. And so now it's a question of, do I know my derivatives of exponent functions? So b prime of t, that first 16 just becomes 0 for the derivative. That negative 16 is a coefficient, so I write that first. And then the derivative of anything with e in it is, first you take the derivative of your exponent. Derivative of negative 0.4t is negative 0.4. And then times the original e to the negative 0.4t. So the two negatives do make a positive. And 16 times 4 would be 64, so 0.4 would be 6.4 times e to the negative 0.4t. There's our derivative. And if we want it at t equals 5, then you would just write 6.4 times e to the negative 0.4 times 5. You only have to simplify this as much as humanly possible, which means the only thing you can do right now is multiply 0.4 times 5. You'll get negative 2 power. This is one answer. You could also write it like this, 6.4 over e squared. because negative exponent means it can go in the denominator. Both are right in my opinion. And since it was the rate of change, this is ounces per minute. Okay, is there anything else that they wanted for this problem? I think we're good. Okay, so now let's check our answers with the results for number 3. Okay, part A, 1 point for the approximation, 1 point for the units. Our approximation, 1.6, that's exactly what we had. Units, that's also what we had. Part B, look at this. 1 point for using the mean value theorem, C of 4 minus C of 2 over 4 minus 2. And 1 point for the conclusion using mean value theorem. They also said that C is differentiable, therefore C is continuous, therefore, on the closed interval. I think you do need that for your justification of mean value theorem. You do need to say that. Okay, so this is exactly what we said, so I think we're good for part B. Part C, you get 1 point for the midpoint sum, which they got 10.1 ounces. That's what we got. Oh wait, I have this backwards. The midpoint sum was 60.6. The approximation when you divide by 6 was 10.1. So there's 2 points right there. And then 1 point for the interpretation. Look at this. Average amount of coffee in the cup in ounces over the time interval from 0 to 6. We forgot to say the time interval. I feel like I would have lost a point for that because the time interval is important. And then part D, 1 point for the derivative, which this is what we had, and 1 point for our answer. You'll notice they wrote it with e squared in the denominator, but again, I think they would have accepted this answer as well, 6.4 e to the negative second, because it's the same thing. Okay, and that's going to do it on today's video lesson on this type of free response question from the AP exam. So thank you all for watching. If you have any questions, please post them in the comments below. I hope you all have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.